All right, made it back. So for today, we're going to be talking about motion graphs because we're going to have to look at this stuff in graph format as well. So the first kind of graph we're talking about is a displacement time graph. It's got two things. It's got displacement and it's got time. Time is pretty much always going to be your independent variable. So it's always going to be your x-axis, whereas displacement is always going to be your y-axis. All right. Well, we're going to switch out displacement a little bit, but time is pretty much locked in as your x-axis, with one exception much later on. Don't worry about it right now. But so we're looking at displacement time graphs like this. This is how you set them up. But we need to understand what's happening in this motion, right? So remember, displacement is talking about where it is. So when we're starting right here, this means we're starting at the origin, right? So we're starting at 0. And as we go along this line, we want to think about, are we moving? Are we moving, yes or no? The answer is yes, we're moving. Our displacement's changing, right? So we moved up to 5, and then we start the next leg of our journey. So when we're going from here to here, the question is, are we moving? Yes or no? What do you think? We are not moving, so there is no motion right here. How do we know there's no motion? Well, the displacement doesn't change. It stays at 5. So if you think about, like, we're on a number line here, a wonderful straight number line. So 1, 2, 3, 4, 5. So in our first part, we started at 0. And then we walked up to 5, and it took us 5 seconds to do it. Now we're just sitting here, right? We're staying at 5. Nothing's happening here. So a flat line on a displacement time graph means that there's no movement occurring. Now, once we go on this part, we're going to go downhill. So are we moving? Yes or no? What do you think? Yes, we are moving. There is motion, but it's different. What's happening compared to what is in the first half? What do you think? There are two possible answers here. One, we are moving backwards. Well, we'll call it backwards. We're moving this way now, right? And we are moving faster than we were in the first half. How do I know we were moving faster? Well, we're covering the same distance, right? Still going 5, but we have a shorter amount of time to do it. We've only got, we'll say, 2.5 seconds instead of 5 seconds here. Okay, now we've been dancing around this topic here. So when I was talking about you're moving faster, you can look at the graph and know that right away. The reason is because if I take my displacement is my y, and I take my time is the x, I can divide them, right? And I get y, well, delta y over delta x. Now, that's just slope. Now, in our case, the slope is the change in y, which is displacement, divided by the change in x, which is time. Now the displacement over time is equal to velocity. So what we know from this is that your slope is going to equal your velocity. So that's why you have some velocity here, because you have some slope. Here, your slope, I'm gonna use m for slope because mx plus b. Your slope is equal to 0, so your velocity is equal to 0. And in this one, your slope is negative, so your velocity is negative. Ta-da! So that's pretty much all we can talk about for displacement time graphs. Now, this one didn't have it, but you are allowed to go negative, right? If you went in this area at all, but it didn't show up for this particular graph. All right, there's one other type of graph that we have to worry about. Let's look at that. This is a velocity time graph. Okay, so velocity time graph, I wonder what makes it different. It means that this area right here is your velocity, and it's going to be in meters per second. On the x-axis, you're still going to have time, and you're still going to have seconds. When you're doing anything with numbers here, make sure you have a unit, right? So, For a velocity time graph, let's talk about what's happening. So between the origin and A, the question is there motion in this part? Yes, there is motion because the velocity, you have a velocity, right? It's not zero and it's changing. So you are speeding up as you're going up here, right? Because your velocity starts at 0 and then your velocity is going to change to 10. Okay, so after that, let's look at the next part, A to B. All right, so A to B is this guy right here. The question is there motion from A to B? There is motion. Now it is going to be constant motion, so this has a constant velocity. All right. So this means you're just cruising along. You're not speeding up, you're not slowing down because the velocity is at 10 and it's going to stay at 10 for that whole region. All right. For B to C, is there motion? What kind of motion is it? Sorry, you'll have to talk louder. I can't hear you. But maybe you said that there is motion and it is accelerating, or it is an increasing velocity, right? Sorry, I didn't mean to drop the A word there. So you are increasing your velocity as you go up because you're starting out at 10, you're going to 20, you're moving. What about from C to D? What kind of motion is there? See if you can describe it to me. All right, there is motion. Of course there is. What kind of motion is? You are slowing down. Right? You're slowing down to a stop even because your velocity is dropping all the way down to 0. Now it doesn't look like it, but let's assume that the line keeps going right here. Is there motion in this part of the line? No motion. There is no motion in this part of the line. The reason is because the velocity is 0 and it stays at 0, so you are still. You're at rest that whole time. Now, just like before, the slope is meaningful in this kind of thing. So remember, if I want to talk about slope, the slope is going to be whatever is in your y divided by whatever's in your x. You know, x1 minus x2 kind of thing. So, what's in our y here? Our y is in velocity, and our x is in time. So if you have velocity divided by time, that is acceleration. So your slope here is equal to your acceleration. Now that makes sense. You have a positive slope in that first region because you're going up. Here you have no acceleration, but you do have a constant velocity. On this downwards one, you have a negative acceleration because you're slowing down, and here you have 0 acceleration again. All right. So here we've got a couple different graphs here. So one thing that we'll be doing is we'll be asking you who, all these different, pretend they're cars, who is the fastest, we'll say speed, sure. Okay, so who's traveling the fastest for this kind of stuff? Well, there's two legitimate answers here. B is a good one. B is an answer. Definitely. It is cruising uphill like that. A is not moving, right? Because no distance is changing. D could be going fast at the end. Well, I suppose it's a poorly written question. My apologies. B has the fastest average. B, well, and C, because they both cover the same amount. B and C have the most average speed, highest average speed, but it looks like D has the highest instantaneous speed. It looks like E maybe at the beginning, but it's hard to tell without some more data on there. So D and E have the highest instantaneous. All right. Who's not moving? A is not moving. Other questions they might ask. Who has acceleration? All right, so which ones of these have acceleration? Well, acceleration means you're going to have a change in velocity divided by time, right? Forget about the time right now, but you got to have a change in velocity. Well, change in velocity, velocity is slope. So you got to have a change in slope. There's only two of them that do that. It's going to be D and E. All the other ones are straight lines, so they're going to have constant velocities. All right. Sounds good. They could ask other specific questions. We're not going to worry about that right now. There's one more set of graphs we're going to look at, because those graphs are going to be velocity time graphs. A, B, C, D. Okay. So let's say we're in a race. Vroom, vroom. Who wins the race? Who's going to cover the most ground? The fastest. All right. Well, let's see here. We've got an A, B, and a C and a D. Hopefully you can eliminate two of them right away. So the winner of the race is going to be A. Okay. How do we know that? Well, it's about who covers the most distance the fastest, right? So I'm going to ask another question first, and then we'll come back to this, how I can tell you that it's A. All right. So who travels the fastest at the end? And it could be more than one thing. By fastest, we'll say highest velocity, if you know, to clarify. All right, there's see if you know. Okay, let's see. It looks like there's two answers. There's going to be an A and a B. Now, since A and B, now to come back to that first one, right? A and B have the same ending velocity, but if I look at A, I'm going to just graph A real quick because he was a straight line. A was traveling faster for the whole race than B was until the end when B tied it up. If the race kept going, then B might pass it. But because of that, A is going to cover more distance because it's traveling faster for longer. Okay, there's something else in here too. Now, let's say I wanted to know what's the distance A covered. Well, how do you calculate distance? Distance is equal to velocity times time, right? Because velocity is equal to distance over time, you know, doing some solving there. Now, velocity times time. Velocity is your y variable here. Time is your x variable here. To do that, that is going to calculate area in this graph here. Okay, so to figure out the distance of A, that's going to be the area of this triangle. Okay, so it's going to be 1/2 this times that. Whatever numbers. I don't have any numbers for this one. Now, you could do the same thing here. It's a curve, so it's not going to be clean or anything until you know calculus. But it's easy to see that there's more area for A than there is for B. So A is going to cover more distance than B is. Okay? What's happening to C and D? Let's see. Well, what we know about C and D is they are going to be going backwards, right? Because they have negative velocities here. All right, let's ask another question. So who has acceleration? Now, there's going to be, yeah, so who has acceleration? There are two people with acceleration. There are more than one people with acceleration. It is actually everyone has acceleration. Cheap shot? Maybe, but you know, we're just trying to ask the kinds of questions you're going to see. How do I know this? Because everyone has a changing velocity. A, B, C, and D. Now, B and D, maybe you said B and D, okay? Whoop. B and D, they have a changing acceleration. Okay? So they have a low acceleration here and a higher acceleration at the end. Okay? We're not going to deal too much with that kind of motion here. It's not really that bad, but calculus spells this all out for you. A and C have a constant acceleration. Right? They have a constant acceleration. We know this because they have a constant slope. Okay, so hopefully this helps you with the graphs here. You're gonna see some